All right, so we're at the point in our semester when we can't go any further without defining what we mean by vector space. And vector spaces really are what linear algebra is about. It's what linear algebra studies. By definition, linear algebra is the study of vector spaces and linear transformations that connect those vector spaces one to another. And so that's it, full stop. And what's great about this definition is also what's frustrating about this definition, is that it's not very concrete, right? It tells me what properties the addition-like operation and the multiplication, scalar multiplication-like operation need to satisfy in order to qualify those operations as being operations on a vector space that are eligible to be studied by linear algebra. And so there's this list of 8 properties that a vector space needs its operations to satisfy. And they seem like common sense things. And the reason they seem like common sense things is that these are generally operations that the standard real number system with the standard operations of addition and multiplication already satisfy. So it's learning about abstract algebra, and this is an element of abstract algebra that we're talking about. Those of you who are math majors, abstract algebra proper is the course that comes after this one, so maybe you're registered for it in the fall, for example. And it really is the straightforward, straight-ahead study of algebraic structure as such, right? And so you have some concrete examples, but we use them just to illustrate these general principles. And so in abstract algebra, it's a bit like trying to learn what your tongue tastes like, right? We sort of are trying to teach a fish about water. Like it swims around in it all the time, but it's probably not conscious of it because it's just always there, right? Same thing with the properties of the real number system and real number arithmetic. These things are obvious. We've learned them for a long time ago, but now is our chance to actually look at them as things that are not necessarily guaranteed to us if we monkey around with the definition of what addition is supposed to mean, or the definition of what multiplication is supposed to mean, or even the very nature of the objects that we are adding or multiplying by one another. But anyway, these are the 8 properties. The addition operation has to satisfy these top 2 properties, which are associativity and commutativity. So associativity says if I'm adding 3 of my vectors together, 3 of my elements together, that it doesn't matter if I add the second pair and then I add the first, or I add the first pair and then I add the last, that those answers are going to end up being the same. So we can move those parentheses anytime I have addition followed by addition. Commutativity is the second one. It says that the result is the same if I reverse the order in which I'm adding to the same thing. So v plus u and u plus v give me the same answer. And then the third one is the existence of an additive identity. So there is some element that in this definition is being given the placeholder name of z. It's meant to invoke our sort of mental picture of what 0 looks like with respect to ordinary addition. And the property that it has is that no matter what vector v that we add to our z, the result is just gives us v back again. So adding this z element is an invisible operation. It doesn't actually change any vector that it adds to. So just like 0 doesn't change any number that it adds to. Also additive inverses. For every vector in our space, there also has to be another vector that if I add those 2 vectors together, their sum is equal to our additive identity. Their sum is equal to 0. And we write that additive inverse as minus v, again, to call to mind the idea of x and minus x, like 5 and minus 5. If I add those together, the result is 0, which is the ordinary additive identity. So those 4 properties have to do with just the addition operation so far. And then the next set, we're going to look at how multiplication is supposed to work and also how it's supposed to interact with addition. So one of the things that you notice about the numbers 3 and 4 here is that the definition of additive inverse relies upon the existence of an additive identity. So if the additive identity part fails, then it doesn't really even make sense to discuss what an additive inverse would be, right? So we either have both of them, or if we only have one, it would be property number 3. So as an example of a structure that would have property 3 but not property 4, think about, for example, the set of all non-negative integers, right? 0, 1, 2, 3, 4, 5, and so forth, with the ordinary operation of addition. Right? It has an additive identity because 0 is there, and if I add 0 to any of my non-negative integers, it's not going to change that non-negative integer. But we don't have any additive inverses because there's no number I can add 5 to, for example, to get 0 as the sum, except for negative 5, which isn't a part of that set. Right? So we can have property 3 without property 4, but we can't have 4 without 3, right? If that makes sense. The multiplication operation, and remember, multiplication here is not multiplication of vector times vector. It's multiplication of vector times scalar, so times a single number. We don't have to be able to multiply vectors by one another. In general, we can't in a vector space. Most vector spaces don't allow that. Vector spaces that do actually get a different name. They're called algebras, and they're not something that we study usually in undergraduate algebra courses for whatever reason. Anyway, so multiplication is multiplication of a scalar times a vector. And the properties that it has to have are also associativity, that if I multiply a vector by a scalar and then multiply that result by another scalar, it's the same as if I had multiplied the two scalars first and then just multiplied the vector by their product. Right, so that's property number 5. Property number 6 is that this is worded kind of weirdly, but it's worded weirdly, I think, for a reason. We need to have an existence, like a multiplicative identity has to exist. There has to be something which, when we scalar multiply it by a vector, that multiplication is an invisible operation, right? To scalar multiply by this identity doesn't change any vector that it's multiplying. And they give it a specific name here. They call it 1. Again, because this is the role that 1 plays with respect to ordinary multiplication of real numbers, right? But I think the reason they get away with being concrete here is that we're talking about scalar numbers. And scalar here generally means it's something that could be the magnitude of a vector, right? It gives us a sense of the scale, the size of a vector. It can make a vector larger or smaller, right? But it can't change its direction. That's the idea of scaling. And so generally scalars are thought of as being real numbers or complex numbers as far as most ordinary linear algebra courses go. But when you move on to abstract algebra, scalars can also be elements of other what are called fields. So fields are just arithmetic structures where you can add, you can subtract, you can multiply, and you can also divide by everything except for 0. And that all of those operations of addition and multiplication are commutative, associative, they distribute over one another, they have all the wonderful properties that you need. And so you can do, for example, linear algebra where your scalars come from like the ring of integer, the field of integers modulo 47 or something like that. Right? You can have a modular arithmetic field as being the base field for your vector spaces, and if you want to do something like cryptology, for example, that is a really important thing to be able to do because your codes and your ciphers often have a finite length of your ciphertext, and that length is going to define a certain modulus on the arithmetic in your scalar field, and so you end up doing linear algebra over these finite fields if you do cryptology. Anyway. So we will take it on faith, though, that 1 actually means 1. I think this is the one place where I can sort of point at it and say, yeah, this actually means what you think it means. Everything else on this slide, maybe not, right? We can monkey around with it. And finally, properties 7 and 8 tell us about how the addition and multiplication, scalar multiplication operations interact with one another. And in both cases, there is a distributive property that does the thing that you would want it to do, right? Which is that if I add two vectors, quote unquote, and then I multiply the result by a scalar, it's the same as if I'd multiplied each of those vectors by that scalar and then added the results of that. And then conversely, if I add the scalars, and this plus is actually real plus, right? This is actually real addition because it's connecting a scalar and a scalar, right? So this is really addition of real numbers or addition of complex numbers. And then I scalar multiply a vector by that sum. It's the same as if I had scalar multiplied that vector by each of the summands and then added those two results together. So this set of 8 properties, if I have a set of elements, call that set capital V, and I have an operation, a binary operation that we're going to call addition, and a scalar multiplication operation, we call it a group action of the field of scalars on our set. If I have those 3 things, then if they satisfy these 8 properties, we can call that structure a vector space. And as soon as I can call a structure a vector space, I can do linear algebra on that structure. So all of this is generality. What are you actually asked to do in this section? So let's take a quick look at activity 2.1.2 over here, where what we're given is a set of elements which are points in the xy plane, and they're points that satisfy y equals e to the x. So these are points on the graph of the function f of x equals e to the x. And on that set, we define a new type of addition of 2 points, of 2 elements of my set, and a new kind of multiplication, scalar multiplication, for elements within my set. And take a look at what it's doing. So this operation is being defined as if I take one element x1, y1 and another element x2, y2, and I add them together, then what I'm doing is I'm actually adding the x components, x1 plus x2, But my y components, I'm actually going to multiply instead of adding. So this is my new definition. This is like the new spin on addition. Same thing with scalar multiplication. If I have a scalar and I multiply it by x1, y1, that I'm actually going to multiply the scalar by the x component, but the y component I'm going to raise to the power of that scalar. So it's a very different kind of operation. Rather than just multiplying both components by the scalar in order to do the scalar multiplication, I multiply the first component, but I exponentiate the second one. And so the goal here in this piece of the activity is to show that this structure actually satisfies the distributive property. So this is the distributive property number 8, right? The distributive property of scalar multiplication distributing over scalar addition. By simplifying both sides and verifying that they give us the same answer. And then also the part B, show that there is an additive identity. So this is property number 3. By choosing appropriate values for what we should see, what should the components of the z vector be, in order that property 3 is satisfied. Namely, for any vector v, we have v plus z is equal to v itself. So that's the task.